So this is an important topic because so far we've talked a lot about heat flowing from gases and solids and so on, and the effects of heat flow on those systems, but I haven't told you anything about how does this heat travel. So if I've got a system at a high temperature connected to a system at the low temperature, through what physical mechanism does the heat transfer? What is the physical mechanism behind the transfer of heat? Okay. And, well, there are three main mechanisms, three main ways in which heat can flow, and these are known as convection, conduction, and radiation. So I want to talk briefly about each of those for the rest of the class. So the first one is conduction. This is transfer of heat by the exchange of vibrational energy between neighboring particles. So you can think about it in the following way. Suppose I've got a block of stone or whatever, and suppose that one end of the block is hot and the other end of the block is cold. So if this end of the block is hot, it means that the particles in this end of the block will have quite a lot of energy, so they'll be vibrating quite strongly. Okay? This end is hot. Whereas on this end, the particles have a small amount of energy, which means they'll only be vibrating much less. Okay? Now, as a particle here vibrates, it will excite the particle next to it. So this particle has a high energy, so it vibrates a lot, and therefore the particle next to it starts to vibrate. And through these interactions, this vibrational energy is transferred from one end to the other. So this is at high temperature, so the particles have a lot of energy, and they transfer this energy through interactions along the solid. So this is called transfer of heat by conduction. Neighboring particles interacting with each other transfer their kinetic and vibrational energy. So that's one type of conduction. There is another type of conduction which is only in metals. Metals have what are known as conduction electrons. These are electrons which can travel over the whole of the metal. They are free to move. And these electrons can also transfer energy. So if I have a fast-moving electron in one part of the metal, it can move to another part of the metal and thereby transfer the energy. This is transfer of heat by the motion of conduction electrons in metals. Okay, so now we want to be able to quantify this mathematically. How do we quantify the rate at which heat flows by conduction? Well, we can do it by something known as the thermal conductivity, which I will now define. So the setup is this following. Suppose I've got a block of something, a reservoir, which is held at a constant temperature T1. I then connect it to a slab of my conducting material, which may be a metal, or it may be a block of stone, or it may be a box containing containing a gas. Whatever, it doesn't matter. And on the other end, I connect it to another box, another reservoir, which has a fixed temperature, T2. So I'll suppose that T1 is greater than T2. So in this case, there will be a flow of heat from this part to this part, dQ by dt. So the thermal conductivity of this conductor here tells you how much heat will be transferred from here to here. So how big is dq by dt? Now it depends upon various things. It depends upon the area of the connecting surface, which I'll call A. So A is the surface area. The area of the surface connecting the conductor to the reservoirs. And it depends upon the length of the conductor here, which I'll call L. And clearly it depends upon the difference in temperature between the reservoirs. If I have a bigger difference in temperature, I will get more heat flow. So the equation is the following. The rate of heat flow in this system is, well, first of all, the area. If I double the area, then it will double the rate of heat flow. If I double the area, I double the number of atoms through which the vibrational energy can be transferred, for example. And therefore, we would expect that the heat flow should double. So firstly, it's proportional to the area. Secondly, if I double the length of this conductor here, if I double L, then the heat flow should be slower because it has more substance to transfer the heat through. So therefore we expect that the rate of heat transfer will be inversely proportional to the length of the system L. And finally, the higher the temperature difference, the faster the heat should be transferred. And again, we'd find that the rate of heat transfer is proportional to the difference in temperature. Okay. So that's the physical parameters. And there's some constant here, which is usually given the symbol kappa. And this is known as the thermal conductivity. And this is what characterizes the system. Okay? So if kappa is a very big number, then that means you will have a high heat flow. So if kappa is large, you will have a very large flow of heat. If kappa is small, then the flow of heat will be small. Okay? The rate of heat flow will be small. Okay? So I want to give you some examples. I'll show it down over here. If we look at copper metal, then you find that kappa is approximately 400, and its units are joule per second, that's dq by dt, per meter, per Kelvin, per difference in temperature. Okay. So that's an example of a high thermal conductivity. If we look at something like glass, then kappa is approximately equal to 1 joule second Kelvin. And if we look at something like air, this is air at atmospheric pressure and temperature, then we find that kappa is approximately equal to 0.03 joule second meters Kelvin. So this data illustrates some important points. Firstly, you note that copper has a very high thermal conductivity. That means if I take a bar of copper and I heat one end, then the heat will very quickly transfer to the other end. Okay? Heat flows fast in copper. And this is generally true of metals. So if you take a metal, the thermal conductivity is large. And the reason for this is this fact. In metals, you can transfer heat through conduction electrons. And in general, the transfer of heat through conduction electrons is much more efficient than the transfer of heat by exchange of vibrational energy. So because of the conductions in metals, metals have a very high thermal conductivity. They transfer heat quickly. Okay? Compared to another solid like glass, which does not have conduction electrons. So in glass, the energy is only transferred through vibration, then it's much smaller. It's much slower rate of heat transfer. And finally, gases in general have a very low thermal conductivity. The particles are far apart, they're weakly interacting, so they do not transfer energy very well. Therefore, the thermal conductivity is very small in the gas. Now, in gases and liquids, therefore, the most important mechanism for heat transfer is not conduction. In gases and liquids, there's another type of heat transfer, which is known as convection, which is more important. So that's what I want to talk about next. So this is the next type of heat transfer, convection. And this is in things which flow. This is heat transfer in things which flow, i.e. liquids or gases. And it is heat transfer through the motion of particles. This is the heat transfer through the flow of a fluid. And the fluid is either a liquid or a gas in this context. Something which flows. So I can draw you the picture then. Suppose I've got a box which is full of gas, and again I attach it to two thermal reservoirs, one on one side T1, the other side T2, and let's suppose for the sake of argument that T1 is greater than T2. Then heat will be transferred, as before, from the hot to the cold. So it will be transferred by conduction. That means particles here start to vibrate and excite neighboring particles and transfer heat. But because it's a gas, it can do something which a solid cannot. That is that particles in this part, particles close to the high temperature reservoir, can move. In a solid, the position of a particle is more or less fixed. Right? In a solid, it can vibrate, but it doesn't move very much. It stays where it is. Whereas in a gas, this particle here can move all the way around here. And therefore, it can transfer heat through the flow of particles. Now, in the particular cases I've drawn it here, what will happen is that the particles here, which are close to the high temperature reservoir, will conduct heat from the high temperature reservoir. They will therefore get hotter. Now, if gas gets hotter, it expands. That means its density decreases, and therefore it will tend to rise up. So as the particles here conduct heat from the high temperature reservoir, they will expand. Well, the gas will expand. The density will drop, and therefore they will rise up. Over here, when they're in contact with the low temperature reservoir, they will get colder. Heat will be conducted out of the gas. They will get colder. As they get colder, the gas contracts, its density goes up, and therefore it falls. So what you end up with is gas which has a flow, like this. On the high temperature side, the gas is heated and rises up, and on the low temperature side, the gas is cooled and falls. So you end up with this cyclical flow of the gas inside the system. And because the gas can move, it can transfer heat much more effectively than it could through conduction alone. So you find this in a general system. If you heat a gas on one side and not the other, you get these currents formed. Flows of the gas because of the changes in temperature. And these are known as convection currents. Okay, so a couple of systems in which convection is very important. It's very important in the atmosphere, so for example in the modeling of climate or weather. The atmosphere is a gas, right? So the heat in the atmosphere, the temperature, heat in the atmosphere is mostly transferred through the setting up of these convection currents. Okay? And these convection currents in the large scale in the atmosphere are what determines the type of weather that is experienced at different points in the Earth. So this is important in climate and weather modeling. It's also important in the physics of stars. In the center of the star is the nuclear fusion process which generates energy. But in order for the star to shine, the energy from the nuclear fusion has to escape to the surface. Okay? And this is done mostly through convection. So this is the transfer of heat from the center to the surface of a star. The center is hot because that's where the nuclear fusion takes place. And the heat is transferred to the surface where it is emitted as light, mostly through convection. Okay, so that's convection. Unfortunately, I can't give you a nice formula for convection like I could in the case of conduction. This is because convection is a much more complicated process. Okay? In order to understand the kind of currents which are set up, you need a model of the fluid dynamics here. Okay? And fluid dynamics is quite a complicated area of physics. For example, this could become turbulent. You can have chaotic motion in the fluid. It's very difficult to predict how it will behave. Okay? So I can describe what convection is, but unfortunately, I cannot give you a nice simple formula for it. Right. The third and final way in which heat can be transferred is known as radiation. Now this is, well, let me explain. Suppose I've got a system, a box, or whatever, which is at a certain temperature T1. Now suppose that I want to stop any transfer of heat from T1. So if I want to stop the transfer of heat, what would I do is I'd put it in a vacuum. Okay? So I float it in the center of space, and I'd take out all of the air around it. Then no heat can transfer by convection, no heat can transfer by conduction. Okay? But even in a vacuum, you still have the transfer of heat, and it's the transfer of heat through radiation. And this is the one form of heat transfer which you cannot stop entirely. Okay? So what is it? If you've got a body of a certain temperature, it will naturally by itself continually emit electromagnetic radiation. So this is the transfer of heat by the emission of electromagnetic radiation. Okay. In other words, light. So you can actually see this process happening in certain situations. For example, the sun, when you look at the sun, it's bright, right? The sun is bright because it's giving off light. The reason it's giving off light is because of this thermal radiation. The surface of the sun has a certain temperature, about 6,000 degrees, and it therefore glows. It emits radiation. Another example is if you have a barbecue and you put coal in the bottom of the barbecue and you set it on fire, then after the fire has gone out, the coal will still glow red. So after you put the barbecue out, you still have red glowing coals. This is because of this. You heat it up, and it therefore emits electromagnetic radiation. Now, in fact, this is true of everything. So as I stand here, I am also emitting electromagnetic radiation, but you can't see it. You can't see it because I'm colder, and therefore the wavelength of the electromagnetic radiation is longer. So people and animals, warm-blooded mammals, emit radiation in the infrared region. So we can't see it, but you can get night vision goggles and so on, which can allow you to see this radiation. And certain mammals can see it. And this is true whatever the temperature is. So even if you go down to very low temperatures, you will still emit radiation, except the wavelength of the radiation will be very long. Okay. Now, transfer of heat by radiation, I can give you a nice formula for. It says the rate of heat transfer is equal to some constant times sigma times, so another constant times epsilon, which depends upon the properties of the body, times the surface area of the body, times the temperature to the power 4. Okay, so I will explain what each of these terms means. So it's given by this, where, well, first of all, this sigma is just a constant. And it has a well-defined value of 6.5, a well-known value of 5.67 times 10 to the minus 8. Units are watts per meter squared per Kelvin to the 4. And this is known as the Stefan-Boltzmann constant. The value of this constant is predicted by physical theory, and if you listen to the follow-on course to this, the Yolmit Tonge Mulihak E course, we will prove why the constant has this form and why this equation has this form. Epsilon is a property of the body called the emissivity. Okay. And it takes values between 0 and 1. And it tells you how well this body emits radiation. If it's close to 0, then it means that the body only emits a very small amount of radiation. If it's close to 1, then it means that the body emits close to the maximum amount of radiation. Okay. So an example of a body which has a low emissivity is if you take a shiny silver foil. Now, it's common in England and Korea, I think, as well, that if you take, as a packed lunch, you take some sweet potatoes or something, or hot potatoes, in order to keep them warm, you wrap them in silver foil. Right? So you take the foil and you wrap them in the foil. The reason you do this is because silver foil has a very low emissivity. So for silver foil, epsilon is about 0.05. This means that epsilon is small, which implies that the rate of heat transfer is small. So if you wrap your potato or whatever in silver foil, then it will maintain its temperature for longer because the heat transfer is less. Okay, so that's the emissivity. A is the surface area. And T is the temperature, which I don't really need to define. So a few important points to note about this formula. First of all, it scales proportionally to the surface area. This means if I take two bodies which have the same temperature, if I take a body which looks like this, and I take a similar size body where I cut out lots of holes in it, so I make it look like this. Let me draw it better. I make it look like this. Hopefully that's clear. So I take a body and I take this body and I cut lots of holes out of it, so I get something which looks like a comb. Okay. Now in doing this, this one has a small surface area, right? It's just that distance around there. Whereas this body has a very large surface area, because the surface area of this body includes all of these little holes. Okay. So therefore a body which looks like this will lose heat much faster, okay, because the rate of heat loss is proportional to the area of the body. This one has small a, and this one has large a. So therefore, if you want to design a body which loses heat quickly, it's a good idea to maximize the surface area. And you will see, for example, if you go to the Nicolguan in this university, in Nicolguan, they heat the rooms by using radiators. And if you look at the shape of the radiators, which are along the side walls in the rooms, they look like this. Okay? The radiators have lots and lots of small pipes. And the reason is, by doing this, you maximize the area, and therefore you maximize the rate of heat transfer. So you heat the room faster. Another example of this is, if you look inside a computer, the chip, the CPU, gets very hot, because it's doing a lot of computation. And often, if it gets too hot, it will stop working. So on top of the CPU, you put something which looks like this. Okay? This is also called a radiator. And the reason you put something like this is it has large surface area, and therefore it maximizes the rate of heat transfer away from the CPU. That's that. The other point I wanted to make is the power 4 here. Okay? In the formula for conduction, the rate of heat transfer was proportional to the difference in temperature. Whereas here, the rate of heat transfer is proportional to temperature to the power 4. That means that this radiation is generally important at high temperatures. If I take a big number and take it to the power 4, it gets much bigger. So radiation is much more important at high temperatures than conduction, because of the power 4 here. So there are some bodies which have a particular special property. Those bodies for which epsilon is equal to 1, which maximize the rate of heat transfer, are known as black bodies. Bodies with epsilon equal 1 are called black bodies. Okay, not because they are black, right? They don't look black, but this is just a technical term for them. They're called black bodies. And these bodies, we can predict very accurately what the spectrum of radiation will look like. Have a characteristic energy spectrum called the Planck distribution. So this means if I plot the amount of energy in the electromagnetic energy per unit time in the emitted radiation as a function of frequency, then it follows a well-known form which is called the Planck distribution, and it looks something like this. It's roughly proportional to frequency squared here, and it decays exponentially on the other side. And it's the peak of this distribution here which determines the color of the body. In other words. For example, the coal in the barbecue looks red because the peak frequency here corresponds to red light. If you go to a hotter temperature like the sun, then the peak frequency is higher, and therefore it corresponds to something like yellowish light. Okay? So you go to higher temperatures still, you change the colors. So for example, very hot stars look blue, because if the temperature increases, the frequency increases, and then you get, if this is red, you go red, yellow, green, blue. So hot stars tend to look bluish because they peak at a higher frequency. Okay. Oh, and I should say, for example, the example of stars is important because stars are very, very nearly black bodies. And this is a fact which is very important in astronomy. That means that by looking at a star, just by looking at the light it emits, we can determine its temperature. Stars are very nearly. They're not quite, because they have some absorption lines in the spectrum. But they're very nearly black bodies.